Assalamu alaikum. I'm Mr. Rajibur Rahman and I will be discussing about series clipper circuits today. The reference textbook for this discussion is Electronic Devices and Circuit Theory by Robert Boylston. So what is a clipper circuit? Clippers are networks that use diodes to clip a certain portion of the input signal without distorting the remaining part of the waveform. Clippers can be divided into two categories as series clippers and parallel clippers. In the series configuration, the diode is in series connection with the load, and in parallel configuration, the diode is in parallel connection with the load. And based on the availability of another DC supply, both series and parallel clipper circuits can be classified into biased and unbiased configuration. So first we will discuss the unbiased series clipper circuit. Here the diode is in series configuration with the load. So what happens here? During the positive half cycle, as the diode is getting a positive voltage, we will consider an ideal diode first. So the diode will be on and it will act as a short circuit. The equivalent circuit can be represented like this. The output voltage will appear across this resistor R, and here we will apply the input voltage, and we can see the input voltage will be equal to the output voltage here. During the negative half cycle, the diode will be reverse biased and it will act as an open circuit. The equivalent circuit can be represented as this. Here, as the diode is acting as an open circuit, there will not be any voltage appearing across the output resistor. So the output voltage will be 0 volt. Now, if we want to draw the waveforms for this, during the positive half cycle, the output will exactly follow the input, and during the negative half cycle, the output voltage will be 0. And same will be done for the second waveform. We are considering two different waveforms there. So this was the unbiased series clipper circuit. Now we'll look into a biased configuration. Here, there is an additional DC source, and the DC voltage V is forcing the diode to be in the reverse bias state. We are considering a sinusoidal input for this with the peak value of the sinusoidal greater than this DC voltage represented in the figure on the right hand side. So what will happen? The DC voltage source will try to keep the diode in the reverse bias as long as the input voltage is less than this V. Again, I am to mention that we are considering ideal diodes, so there is no voltage drop across the diode when it is on. For input voltage greater than V volt, the diode will be forward biased, and this will only happen during the positive half cycle of the input. So when Vi is greater than V, the equivalent circuit can be represented as this. The diode as a short circuit, and here is the resistor. We'll get the output voltage across the resistor. Here is the input, and this is V. So if we apply KVL here, we'll get this equation. From this, we can say the output voltage will be input voltage minus this V amount of volt. This occurs only during the positive half cycle. Now, during the negative half cycle, the DC voltage source is forcing the diode to be in the reverse bias, and the negative half cycle will ensure that the diode is kept in the reverse bias region. So the negative half cycle equivalent circuit can be represented as this. The diode will act as an open circuit, and we will not get any output voltage here. The output voltage will be 0 volt here. So if we want to draw the waveform for this configuration, we need to consider the case when V input process the constant DC source V. Only after that we will get an output voltage, of this form, and the peak value of this will be Vm minus Vn. The output voltage will only be valid across the resistor as long as V input is greater than the DC source C. So we will get something like this here, and during the negative half cycle, the output will be 0. Now we will consider another circuit. This is also a biased series clipper. Here, the 5 volt DC supply is already keeping the diode in the on state. So during the positive half cycle, the diode will be forward biased, and we can represent the equivalent circuit as this. The diode will be represented as an open short circuit, and the output voltage will appear across the resistor. This is the input voltage. Applying KVL, we can show that output voltage will be input voltage plus V. So the output voltage will be shifted amount V, where V is given as 5 volt here. V is given as 5 volt here. So during the positive half cycle, the output voltage will be shifted by 5 volt from the input voltage. Now what will happen during the negative half cycle? During the negative half cycle, the diode will be on as long as the input voltage is greater than minus 5 volt. When the input voltage is more negative than 5 volt, then the diode will be in the reverse bias region, and we will get an open circuit at the diode, and output voltage will essentially be 0. So during the negative half cycle, the diode conducts up to the point when the voltage is minus 5 volt, and after that it goes to 0, and it starts conducting again like this. So the output wave function will be necessarily the wave function that I have drawn here. Now we will consider one more case where we are not considering ideal diodes, we are considering a practical silicon diode here. So for a practical silicon diode, we can consider a 0.7 volt voltage drop across it when it is in the on state, and replace it by an equivalent circuit like this. So this is the same circuit as before. The 5 volt here is greater than 0.7 volt. So the diode will be in the on state here. During the positive half cycle, the equivalent circuit can be represented as this. In place of a diode, we will position a 0.7 volt voltage source. This is the 5 volt input supply, and the output will definitely appear across the resistance R. This is our input. Applying KVL, we can write this equation, which will give us input voltage plus 4.3 volt. So the offset here will be 4.3 during the positive half cycle, and during the negative half cycle, the diode will be reverse biased only when this is less than 0.7 volt, or we can show that Vin is less than minus 4.3 volts. So when Vin is less negative than 4.3 volts, the equivalent circuit will be like this, and we will get 0 at the output voltage. So this will conduct up to the point when the input voltage is minus 4.3, and afterwards we will get 0 here. And this will again start when the input is minus 4.3 and continue like this. So this was my discussion with clipper circuit. Thank you.